So let's get back to our lecture on classification. And just a quick review. The problem of linear classification, meaning that we're going to use a hyperplane to separate our space into two halves. Half 1 here, half 2 here for classes 1 and 2, is that if the data is non-linearly separable, like this one, right, cannot be separated by a simple hyperplane, then we map this into a high-dimensional space where this is, so we can apply a polynomial mapping, for example, like this, that curves my original feature space, and now I can separate these two regions with a simple linear classifier. This is another example using another nonlinear mapping. And note that this hyperplane divides the original feature space, shown here in black, in a way that when reprojected back onto the original feature space, the classifier looks nonlinear, even though the classifier is actually linear, right? It's very powerful. Of course, the problem is this mapping increases the dimensionality of the feature space, and to avoid that, what we did is we defined kernels, right? And kernels are nothing else than changing the metric of our space. So if I have the Euclidean space originally, let's say, right, that it's defined by the circle in 2 dimensions, right, S1, or SP minus 1, the sphere of p dimensions in a p-dimensional space, then what happens is that when I change the metric, that metric changes to, say, the diamond for L1 or whatever we're changing it to, right? And that's the same as warping the space in a way that makes our linear classifier in that warped space look nonlinear in the original feature space, right? And this is a beautiful trick, and because norms, remember, we spend quite a bit of time on that, norms in a Hilbert space, right? I'm assuming I'm always in a Hilbert space here. Norms in a Hilbert space are given by an inner product, right? So when I have my kernel matrix here, where phi of x is, or phi of x transpose, rather, phi of x, where phi of x is nothing else than x, right? Then I have the Euclidean norm, right, or the 2 norm, because this is the vector x multiply inner product with itself, right? So that's the Euclidean norm. When I change phi, then I can obtain a variety of different norms. That is a kernel, and that allows us to redefine the Graham matrix that we had introduced, and that's what allows us to do nonlinear classification with linear methods. And then the question is, okay, how are we going to do this linear classification in that intrinsically higher dimensional space? And note that I say intrinsically because I'm not changing the dimensionality of the feature space, and that is a point that needs to be reiterated over and over and over again. We are not changing the dimensionality of our feature space, only intrinsically by changing the norm, okay? Okay, so we need to find this vector that is normal to the hyperplane that defines my hyperplane. And we said that there's this solution space, right? Any vector A that is defined in that solution region is a solution for classifying my samples. And the way we're going to find this is by defining a criterion J that we're going to minimize, right? And how do we minimize this criterion? By taking the gradient, right, the partial derivative of that criterion with respect to its parameters, and then just following the gradient. This is the algorithm that we've derived before, Newton's method, remember, when we derived Newton's method, which uses both the gradient and the Hessian, right, matrix. And the Hessian is nothing else than the second derivative. And what's the second derivative? It's the acceleration, right, of my function J, right? Now, the higher the acceleration, right, the higher the degree of acceleration in my function. So say that I have a function that looks like this, right? Versus a function that looks maybe something like this, right? This one has a much higher second derivative, right? And I want to be more careful when I advance, when I add a step forward, because if I follow this gradient here, if I am to follow this gradient from here to the next step following the gradient, I may go too far in an area where maybe this curve is now like this, right? And now I pass my minimum, right? It could even be worse. It could be something like this. And now I end up with an area where I've actually missed the minimum I'm looking for, right? Whereas here, if I am to use very small, so here it's better to use a smaller advances, right? This is why this is inverse. But here, if I keep using very small changes, then I'm never going to reach the minimum. It's going to take me forever to do that. So when it's more shallow, you want to go faster, right? So that's what, in general, we called the learning rate here, right? This function nu that changes with respect to, or that determines how fast I'm moving. And Newton's method just uses the equation to do that. So that's where we were defining the perceptron. The perceptron is one of the simplest, if not the simplest, method or criterion that you can define. And the criterion is very simple. You take all the feature vectors that are currently misclassified by a given initial value for A, and then you compute negative A transpose Y, right? Because that's what you want to correct for. And then you add this to the criterion, you sum it over. We take the derivative with respect to the parameters, which is A in our case, and we obtain negative Y, right? So that's our gradient that we add here, and that's the function that I want to use. So this is a simple algorithm for the perceptron, right? The new A is the previous A plus that increment that I'm going to add here. Okay? Now, this is the perceptron criterion that we have derived thus far, right? So if you see the gradient function here, right? If you compute the gradient, you will see that it doesn't matter where I start in that feature space, right? I will always end up in this region down here, right? The minimum, which is my solution region. So it's perfect. So that actually leads us to this famous perceptron convergence theorem, which says that these algorithms always guaranteed to converge if the data is linearly separable. Okay? If the data is not linearly separable, good luck. Right? It's not going to converge. The point here is that it's eventually going to converge, obviously, right? Within that region, but we don't know where in that region, right? And as we'll see today, that is important, or that could be important, right? So we'll first see that it is important, then we'll see that it's probably not that important, and then we'll see what to do. Again, we're going to try to work this out a little with more math, more formally, I mean. All right, so that first algorithm that we derived, or that we defined, rather, in our last lecture, uses the symbols that I misclassify. But it does not include that margin. So let's see how we can include the margin, right? So if I want to include that margin, what do I want? I don't want this to be equal to 0, right? Or smaller than 0. I want it to be smaller than that margin, right? That's what I want to do. And then what we're going to select is the B value. This is the new parameter that I have now, right? That improves over my classification. Okay. So another way to do that, and we're going to get back to this in a second, okay? Another way to improve is by considering the positives and the negative weights of the vector A separately. And then do corrections on the positive weights are made only when one or more training patterns or samples that should be in W1 are misclassified. Remember, W1 corresponds to class 1. And corrections on the negative weights, right, which are on the negative side of the hyperplane, right, when I do W transpose, or A in that case, A transpose X, right, and I'm on the negative side, then those are only going to be changed when samples from W2 are misclassified. So let's see how we can take advantage of all these things. We're going to do a what's called relaxation procedure here. The perceptron criteria described above, meaning the observations that we've given thus far, can be changed to this one right here. And what's the difference that you see here from what we used before? What is this criterion right here? It uses what loss function? The square loss, right? What's that? It says right. Oh yeah. So even better, right? You should be able to say it. You just read. So you can just use the square loss, right? Why would I want to do that versus don't read? Why would I want to do that instead of using the function that I had before? Because it's a smoother function, right? It's a continuous function. It's going to give me a smooth gradient. So let's go back to here, right? And let's look, or actually here, and let's look at this perceptron function, right? What do you notice that is probably not very convenient if I want to maximize that margin, right? I want to add some margin here. So I want to get away from these solutions that, you see this one? I may end up here, say, whoops, okay, I'm already in the solution area. I stop. Why do I stop? Because this region is flat, right? There's no gradient. Once I'm in this solution area, I'm stuck there, right? There's no way out of it, okay? But that's also true, that could also be true in many other places, right? There could be saddle points in my function, and once I reach a saddle point, it's like reaching a minimum or a maximum. It doesn't matter, there is no gradient there, I'm stuck. There's nothing I can do. So what we can do is go back to the square laws, and then when we compute the gradient of the square laws, we're going to get something that looks much smoother. We can also add, because another problem with with the criterion that we had before is that it's dominated by the largest training vectors, right? Remember that we mentioned that when especially we talk about PCA and LDA, right? That we said, well, it's a problem where with the square laws when the samples that are farther away are squared, they have so much more relevance, right? And that can be sort of solved by normalizing by the square of the y vector. So if you take now the gradient, this is the new gradient that I have, and this then is a new update function that I have to work with, right? And here are the two different functions that I have defined. You see this one with the square laws looks much nicer than before, but it's still pretty flat, right? But by normalizing by the y vector size, then I get a more convex region or function that I can apply gradient descent to, okay? So that tends to be our preferred solution because it's going to give us better results. All right, more extensions to that perceptron idea. One is obviously another idea that we have already introduced before, which is called the minimum square error, right, or MSE. Remember when we introduced MSE, minimum square error? So again, what this allows you is, if you remember when the time when we introduce the minimum square error, is that it allows you to find a closed form solution like this, right? So you have all the y's multiplied by the a vector. That should be equal to your b, right? The bias that you want to add, or the h, or let's call it the bias for now. The bias that I want to add to it, that margin. So unfortunately, y, this function, this matrix rather, here y, is n by d, right, or n by p in our case. So it's not a rectangular matrix. So in order to solve this, we need to apply linear least squares, right? So this is our linear least squares error function, which is the same as the minimum square error, right? This is our minimum square error that we defined before. And I'm going to go very quickly through this, because you just take the derivative with respect to the parameters, and you find that the solution is the pseudo-inverse, right? No surprise, you move this to the other side, and you have the pseudo-inverse, right? Y transpose Y inverse times Y transpose, right? It's a pseudo-inverse. And that times B, it's a solution for A. And this is the minimum square error solution. This solution, if the data is drawn for Gaussian distributions, normal Gaussian distributions, homoscedastic normals, I should say, in which case the data is linearly separable, right? In the kernel space, in that mapping space that we have computed, then that would be equivalent to the LDA solution. Same thing. I've added here a simple example for you to look at. With real numbers, you can implement this in MATLAB. It takes like 5 minutes, and you can see how this works, right? Change the values of the vectors here and play with it a little, so you see how this works. Two problems with this MSE is that, as we have discussed before, Y transpose Y can be singular, right? One solution, use PCA, right? So you first use PCA, get rid of all the null space, then apply LDA, or this algorithm that we introduced here, which are going to give you, under some conditions, the same result. The other solution would be to, and Y is generally a very large matrix, right? And that can also be an issue. So we can solve this by minimizing this criterion like this. And to solve the problem, what we could do is to take the samples in this sequentially, right? So because Y is very large, it's a very large matrix, you can just take one sample at a time, right? This is just one possible solution. Now, this is different from the batch perceptron that we have defined here earlier. Where was that? Here, right? Where we take all the samples at the same time, right? Simultaneously. Okay. So these are different examples of this classification. So this is something that is pretty important in classification, and we'll see that there are many methods for deep learning on how, and a lot of debate on how is it better to find this gradient descent solution. Again, one solution is called the batched gradient descent, or batch approach, which considers all the n samples, right? So I have QA, this is our criterion, and our criterion is going to be the result of QA, right, for each of the AIs. I should be probably AI, or, well, the I is here, right, for each of the ith samples that I have, okay? Oh, I'm sorry, this is A, it's the, my mistake. This is the weight vector that defines a hyperplane, and I defines the ith sample here, right? I see how this notation works, right? And this would be the way I define my update function, right? And instead, in stochastic, what's called stochastic gradient descent, which is generally the preferred approach, what we usually call, it's also called online or iterative method, but most people call it stochastic gradient descent. In that case, we compute the gradient as we have shown here on every sample independently, okay? But to be really stochastic, then you have to select the samples randomly, right? So you have two options. You either randomly order the samples at every iteration, or you just randomly sample from the pool, right? You put all the samples in a pool, in a box, and then you just sample them randomly, right? And you apply. And then by doing this, right, this would be the new function that you have. You can, I'm sorry, this one here, you can update for every sample independently. It's an extension of this called the momentum approach, which is a linear combination of this method and the previous method, which will look something like that, right? So you want to add the gradient of the previous step, right? So here I want to consider the previous step that I did plus some contribution for the new step, right? Given by different samples, right? So you get a you carry a momentum from step to step, right? You don't go from advancing 3 points or plus 3 in one of these dimensions, right? In one step, and -1 at the other, right? You have to smoothly move. You have momentum. You carry energy or you carry velocity, right? That you have to account for. See how this works? These are the most popular methods that we'll be using in linear classification, and obviously specifically in deep learning. Okay. This is another approach that is very useful to have for the simple reason that the perceptron finds the separating vector, right, the separating hyperplane, when the data is linearly separable, but does not generally converge when the data is non-linearly separable. So what we can define is a method here, right, that addresses this limitation and actually helps us know when the data in our space is linearly separable or not, right? So let's go back to the MSE criterion. The MSE is nothing else than the minimum square error. And what's the minimum square error? It's y times a minus the value I want to obtain, which is b, right? My bias or my the additional margin that I want to add. So there exists therefore a b for which this MSE yields a solution. However, b, right, is unknown, and that's a problem that we are facing here. And this procedure, right, is a method to search for both a and b simultaneously. And anyone can tell me how I can search for a and b simultaneously here in this criterion? How would you do that? What's that? Yeah, go ahead. So correct, right? So the solution is you compute the gradient with respect to a, right? Partial derivative with respect to a, the partial derivative with respect to b, and then you solve for both, right? Now, because a, this is the MSE criterion, right? Which means that a is going to be solved by the pseudo-inverse, right? So this we can compute in closed form. So which means that we only need to solve for b at each iteration, right? So a at each iteration is given by this equation. Given a fixed b, right, like in the other algorithms that we have seen, we can compute a in closed form and then apply the gradient for b and get a better b and iterate until it converges to a solution. Now, if the samples are linearly separable, this algorithm is guaranteed to find a solution. But importantly, if the samples are not linearly separable, then this criteria is going to be different than 0, right? No matter how long you iterate. And therefore, this algorithm can be used to determine whether your samples are linearly separable or not in that kernel space, right? So that's very useful. All right, another way to do that is with support vector machines. So I'm going to turn to the whiteboard to explain this in a little bit more detail, because this is a very important algorithm to discuss. Very important linear classifier to know about. All right, so recall that a classifier only cares about dividing the space into half spaces, right? And the question that we ought to ask is, what is the best hyperplane that classifies my data? So let's see what we mean by this. So imagine that I have a two-dimensional, as per usual, on the blackboard in p dimensions, right? But I can only draw 2 dimensions. That we have, say, positive samples here on this side, right? The positive side of the hyperplane. And I have negative samples here on this side, right? Right? So far, so good. And now, using the perceptron algorithm that we have introduced here and the variations thereof, right? They're all based on the basic idea of the perceptron. Then I can separate this, or I can obtain, right, given the solution region, vectors, W's, that are going, or A's, that are going to give us maybe this hyperplane, which is a solution, right? This is another hyperplane. This is another, let's see, this is another hyperplane here. This is yet another hyperplane, right? What else? This here is yet another hyperplane, and so on, right? All these hyperplanes correctly separate my training samples, my positive training samples, from my negative training samples, correct? And this is because, remember, in my feature space, there is a region, right, that we have called the solution region, right, that allows us to separate correctly our training samples. And what we have said is, well, what we could do is we can add a margin here, right? A margin B that restricts that my solution be in that center region. And what does this mean in practice? In practice, that means that the vector that is defined right here, right, at that edge of my solution region is going to be a vector that correctly classifies this sample and that sample, but just barely, right? Remember, we discussed this last time, barely. And that, at the other end, right here, is going to be this other extreme hyperplane, right? That barely classifies the data. Now, as we'll see next week, there's no reason to believe that these two solutions are better than any one here in the middle. There's actually no reason to believe that, right? In fact, we know that neither of these solutions is better, statistically speaking. But in practice, let's think about this. In practice, if you were given the chance to select either this solution, or that one in the middle, which one would you select? The middle, right? Because you want to separate the samples that you have as well as you can, right? And what's the one in the middle here? Well, it corresponds to the one that maximizes this margin in the solution space. And that, stated another way, is, let's see, what do we have? 2 positives, another one here, and then negative, negative, and negative here. What this is going to correspond here is to a hyperplane here, right in the middle, such that if I now compute okay, so this is not really the middle, is it? So this one right here, oh, Jesus. All right. Still not perfect. All right, you get the idea, all right? I can only do so. Oh, yeah, that's better. Okay, so the distance between this, B, and this is the same, right? This margin. And the point is that this middle solution here, the center vector, corresponds to maximizing that margin, meaning that there's no other hyperplane you can find that correctly separates this positive from these negative symbols that is going to have a larger margin between the hyperplane and the closest positive and the closest negative symbols to it. Okay? Now, in this case, this is the closest sample to this hyperplane, and these two are the closest to that hyperplane. They're equally close, right? And these are called the support vectors. And they're called the support vectors because these are the ones that support or define that hyperplane that is parallel to my solution plane, right? And that defines the margin. Okay? So now let's see how we can derive an algorithm to find this solution. Okay, so I'm going to use the notation that I have. I have my offset, W0, right? And my vector W that defines my hyperplane. So I have Wx, my sample, as always, plus W0, right? And now remember that if that sample is one of the positive samples, sometimes you'll see this notation x plus, meaning the positive samples. And again, remember, that means that if I multiply x in that equation for a sample on this side of the hyperplane, this gives me a positive number, right? Larger than 0. And if the sample is on this side, it gives me a negative value, right? So for the positive samples, this is going to be larger or equal than some b, right? Some margin. And for the negative samples, I'm going to have this smaller or equal than b. Okay, so given our classical notation, remember we have our xi's, our samples, and corresponding yi's, and we have, say, n samples, right? Xi's in RP as per usual, okay? And then here, we're going to say that yi defines just one scalar that defines either class 1 or class 2, right? And the notation that we're going to use here for support vector machines is that yi is positive 1 if it's a positive sample, meaning on the positive side of the hyperplane. So this is a positive sample. Or you could say class 1 if you prefer. And -1 for negative samples. Or class 2. So what this means is that I can simplify these equations, right? Because now I have my new variable, yi, which is either positive or negative. So what I can do is I can take these equations here, xi w plus w0. This has to be larger or equal than b, right? Right? This is true for positive samples, and for negative samples, I only need to multiply it by -1, so I can add just yi here, and I'm done, right? So this is the equation I'm going to be working with, and if I want to find the hyperplane that divides the data, I could write yi xi w plus w0 minus b equals 0, and that defines my hyperplane, right? Now, without loss of generality, I'm going to assume b is equal to 1. And we'll see in a few minutes why I chose 1, right? It seems like an arbitrary selection. It's not. You'll see that that's actually, there's a reason for selecting 1. But it's just a scalar, right? So we're going to select 1. So now we wish to maximize the distance between the positive and the negative samples. So to do so, we are going to find the maximum of the minimum distance. So find the maximum of the minimum distance. What do I mean by this? From the minimum distances that I have here, right? When I select a hyperplane, I can find the minimum distance. That means the closest that these samples are to the hyperplane, right? That's the minimum distance of the samples to the hyperplane. And what do I want? I want to find the maximum of all these possible minimums given by all the possible hyperplanes, right? Okay. So the width, to do that, we need to compute the width, obviously. The width is given by, let's see, what's the width given by? Well, the width here is going to be given by, for the positive side, is going to be given by xi minus a xj, right? Two vectors, right, that I can have here, times this vector, right? So remember that I can compute the distance, the orthographic projection, with respect to this w by just multiplying it by w. And because w is not the normal vector, I need to divide this by what? The norm. Very good. The norm of w, right? And if we take these positive vectors, I want them to be 1 minus b, or 1 minus b, and the negative vectors are going to be 1 plus b. Then I substitute this here, and I obtain the norm of w. Okay? All right. So what we want, so this is 2w. So what we want is rather, that's fine. 2w. So what we want is to maximize 2w, right? Now, maximizing 2w, or the norm of w, is maximizing the norm of w, right? You agree? I mean, like, there's no difference for that. I did something wrong. I don't know what I lost, but I did something wrong. I want to, sorry, this should be 2 over W, right? So, I mean, there has to be an error somewhere. So maximize this, which is the same as minimizing W. That makes more sense. OK. Now, because minimizing W, the norm of W, it's also equivalent to minimizing the square. True? That's not going to change. I'm going to use the square because, right, that's going to lead me to being able to compute the derivative. And I'm going to add the scalar 1/2. So these two things are equivalent. And how are we going to solve? What method have we seen that we can use to solve this classical linear least squares problem? We saw that when we had, this is the same as the PCA problem that we had, remember? That we want to minimize that square, square loss function. And what did we use to solve that? Well, yeah, but what's the method that we use to do that? When you want to minimize that type of function in optimization, what do we use? Remember we covered that? OK. Are we, let's see, what are we going to do? Are we going to use gradient descent? Are we going to use Lagrange multipliers? Yeah? OK. Yeah. Let's try Lagrange multipliers. So let's see how we can use Lagrange multipliers in our criterion. So what we're going to do is define our criterion here, which is 1/2 of W square, the norm of W square, minus, now we have this function here that needs to be minimized as well. So we're going to add the sum over all I of yi xiw plus w0. What did I say b is equal to? 1, right? So instead of minus b, I write minus 1. Yeah? Correct? And all this has to be multiplied by the Lagrange multiplier, right? And we call them before lambda, I believe, lambda i's, right? So that's how we can solve this minimization problem. And now to find the extrema, the minimum or the maximum of this function, what do I do? Lagrange multipliers. What's that? Okay, the partial derivative. Very good. So let's compute the partial derivative of this criterion L with respect to my parameters W. And let's see, what's this equal to? That's equal to here, I'm going to get W, right? Correct? Because that's why I added the 1/2, right? So the 2's cancel out. Minus the sum over all I of this function. And now let's see what this function is going to be equal to. It's only going to be equal to yi times xi1, right? Yeah. So lambda I, yi, xi, 1. And what do I have to equal this to? Anyone? What do we equal this to? 0. Very good. Find the solution. And from here, we can find our solution. W is going to be equal to the sum of our Lagrange multipliers times yi times xi, right? And this is our first result right here, our solution. And what's interesting about this result, it's something that we saw in our last lecture. What just happened? What's this W equal to? A linear combination of what? Of our samples. Very good. So know that this is exactly the same solution we derived in our last lecture, right? This is the solution is a linear combination of our samples. Pretty cool, right? Okay, so am I done? Am I missing something? These are the Lagrange multipliers, but am I missing something to minimize this criterion here? What's that? Right, W0, W0, right? The bias. So I need to also compute the partial derivative with respect to W0. And this is going to be equal, let's see, this is 0, right? This term doesn't have W0. And this is 1 here. So this is negative the sum of lambda I yi, right? Is that right? Yi times 1, yes. And I equal this to 0 again, and that gives me the other solution, which is that the sum of all over all I of lambda I yi are equal to 0, right? And now I can find my Lagrange multipliers, right? Right here. Okay, so I have these two equations. You see how this works? Okay. All right. So I have this equation here, this equation here. Now let me substitute these two equations into my criterion as we were doing on the slides. So if I substitute these results in our criterion, I get 1/2 of the sum of lambda I, what is it? Lambda I yi xi. Make sure I get this right. Times the sum over all I of, again, the same thing, right? Because this is W, and I'm just substituting W. Where do we have L? Here, right? 1/2 of W square, right? This is W times W, right? Yeah. Minus, now the second part is this one here, which is going to be the sum over all I of lambda I yi xi times, let's see, the sum over all j of lambda j yj xj, right? Is that correct? And now I'm missing one more, actually two more, right? This was for W. Now for W0, I have the sum of lambda I yi W0, and the last one would be just plus 1, right? I have negative and negative. It's plus 1 of the sum of all my lambdas. And if I rearrange all this, I'm going to get the sum of all my lambdas, right? This last term, I put it first here, minus 1/2 of the sum of over all I over all j of lambda I, lambda j, I and j from 1 to n, as always, yi, yj, and the inner product of xi and xj, right? And we just need to maximize this equation. This is our solution. Maximize. We need to maximize this equation. Okay, so let's see if we can make this a little interesting. I have some leftovers from Trick and Treat yesterday. So let's see who wins this. Okay, it's a small prize. So if I solve for this equation, right? This final equation that we've derived, everyone sees that equation? Hopefully I didn't make any mistake. Yeah, is that correct? Now, if I solve for this equation, what are the lambda i's going to be equal to? Who can tell me what the values of lambda I are going to be equal to? If no one wins, I'm eating it. I'm eating the candy. Come on, look at this. What defines the solution? What's going to define our solution? Right, but what's going to define our hyperplane? What's the hyperplane? The hyperplane is given by a linear combination of our samples, right? So what defines this linear combination? Our lambda i's, right? And which of these xi's, yi's are fixed, right? This is the support vectors. So yi for the support vectors are going to be what? What's that? No. Lambda I for the support vectors is going to be what? Huh? All right, let's do this. Lambda i's for the non-support vectors are going to be what? Who said that? Who said that? Raise your hand. You said that? Okay. And can you get the second part? So where the lambda I is going to be? Yeah, you don't turn around. Where the lambda I is going to be for the support vectors? Well, non-zero. Okay, there you go.
It's mine?
Yeah, you got it, right? Oh, it was you? Okay. All right, you decide who got it right. You share it. There are not that many. Okay, so that's a solution, right? That what this optimization is going to determine is a sparse representation, right? A sparse representation of these samples. Yes?
I thought, so W defines the vector
Yes.
pointing outwards, but what,
Yes.
what's what defines the line? How do you actually define the line?
What line?
The actual red line. It's orthogonal to the,
This-
orthogonal to W, right?
It's defined by W and W0, right?
Okay.
The offset and the normal, well, or a vector normal
Right,
to the
because
orthogonal to the plane.
when you're making the classification, you're projecting your x values onto this value, and if it's positive or above that value.
Well, if it's larger or equal than W0,
Right.
right?
Yes.
So forget about the margin for a while. Your classifier really is Wx larger or smaller than W0, right? If this is when I project my simple here, right? This vector W, right? It's this vector here, and that defines this hyperplane here, right? Or this vector, this dimension of the space. Now, when I project this other vector, right, that defines this positive simple onto this, I get this distance, right? And this is larger than W. I'm on the positive side. This one here, right, is going to be projected here, and it's smaller,
Okay, thank you.
right?
That makes sense. I thought we were actually looking at the distance between. It's the same thing, but thank you.
Yeah. Any other questions? Yes.
What if the two classes are not linearly separable?
Very good question. How can we modify this if the classes are not linearly separable?
Can use x by px.
Very good. I don't have more candy, but you deserve candy. Very good. So I changed this to phi of xi transpose phi of xj, where phi is an intrinsic mapping, right? A mapping function, one of the functions that we've defined before, right? That intrinsically maps my feature space, my samples in my feature space into some intrinsically high dimensional feature space where the data is linearly separable. Okay. All right. Now, let's try to justify this a little more. I mean, these equations hopefully are very useful. But let's get into a little bit of, let's dig into a little bit of the details of support vectors. And to do that, I'm going to go back to logistic regression. Remember logistic regression? Simple classifier? Let's go back to that. Okay, so in logistic regression, which I know it's called regression, but it's a classifier, right? In logistic regression, we had the function h, let's call it h, of lambda, right? Lambda, our parameter of x, is equal to 1 over 1 plus e to the power of negative z, where z was equal to lambda transpose x, right? That was the equation that we had, correct? Am I right? And that is that yielded our function that we call the logistic sigmoidal function, right? That looks something like this, right? Well, could be better drawn, but you get the idea. And this is z here. This is h of x, maybe lambda. Specify the parameters. So what is logistic regression really about? In logistic regression, I want x of xi to be equal to our desirable output, right? As always, let's call it yi. So what this means is that we want we want lambda, our parameter, transpose x to be larger than 0 if what? If, anyone? If yi is, is, no, yi, remember, yi is, we have our samples, I haven't changed this. Xi's are in some space of p dimensions, and yi's are either a positive 1 or, well, in support vectors, we usually say -1. In logistic regression, we use 0, right, for the other class, I think. But so that's what we want. So it's going to be positive if this is 1, and it's going to be negative, right, if this is 0, right? Am I right? Now, obviously, in general, right, ideally, you would want this much larger and much smaller because you want to maximize that margin that we were discussing, right? But all you can guarantee is that it's either larger and, excuse me, they're both larger and smaller, and that's all that we guarantee, right? Okay, so let's write this equation down. We can write this as follows. Let's see how we can define this. We're gonna consider over all my samples, I1 through n, I'm going to use the log. Remember the log likelihood because it's just easier to work with, specifically because this is an exponential function. So I'm going to have yi times h of, h lambda of xi plus 1 minus yi, right? Remember the binomial distribution that we defined for the logistic regression, right? Times 1 minus this, right? H lambda xi. So that's the logistic regression classifier that we derived. And we can rewrite this. Maybe let's do this. Let's rewrite this as yi, the log of, actually not equal, but I'm going to change this to the log of h lambda. Oh, I'm sorry. No, I'm wrong. Okay, scratch that. Because I've already converted this into a log. So let's just write it as a log. So yi, the log of h lambda xi plus 1 minus yi, right? The log of 1 minus h lambda xi. Okay, that looks better. And now I can rewrite this as the sum of yi times the log of 1 over, I'm just substituting this by that function, h, right? So 1 over 1 plus e negative lambda transpose xi plus 1 minus yi, the log of 1 minus 1 over 1 plus e to the power of negative lambda xi. This, and now I need to clarify that this is in this summation. Okay. Okay, this is, I haven't done anything new. This is the logistic classifier, logistic regression classifier that we derived, right? using that binomial idea, right? Remember that from our earlier lectures? Okay, so now what I'm going to do, I'm going to linearize that solution. To see this, let's plot the logistic sigmoidal function, right? The logistic sigmoidal function, that was our loss function, right? For logistic regression, that's what we used. And remember that this logistic regression function looks something like this. Actually, yeah. Looks something like this. Let's see. Right? Where this function is, in that case, negative the log of 1 over 1 plus e to the negative z, right? Okay. Now this is when w is equal to plus 1. But what happens when y is equal to negative 1 or 0 in logistic regression? Then I'm going to have something like this, right? The mirror image. And this is negative the log of 1 minus 1 over 1 plus e negative z. And again, this is where y is equal to 0. Yep. That's what we had. Okay, so what I'm going to do here, I'm going to linearize this. I'm going to simplify this by finding another way of representing this. I'm going to have a linear function, right? Like this, or maybe like this here, right? That is linear, easier to define, and then it's going to be 0 everywhere else, right? And let's see how we can write this down. We are going to, we're going to have this function here be equal after some value, right? Here, this is z, right? So after some, I don't know, z null, z0, this function is going to be 0, right? And for this one, before that value, this function is also going to be 0. Okay? And this is a loss function, right? This linearization that we have mentioned before. Anyone remembers what this is called? What's that? The hinge loss. Remember when we talk about loss functions? We talked about this. This is called the hinge loss. Yes, correct. So this is the hinge loss. And now we can use that loss function in our logistic regression here. And so let's see, in logistic regression, we have the minimum of the parameters, right? 1 over n, the sum from 1 through n of yi negative the log of h lambda xi plus 1 minus yi negative the log of 1 minus h lambda xi and plus lambda to n, the sum over all j, 1 through n, of my lambda j's squared. Right? That's what we had. Now, of course, if you will, this n, I can cancel it out, right? Because minimizing with respect to lambda, it doesn't matter. This is just a constant n. That's the number of samples I have, right? So it's irrelevant. So you will see this notation either with n or without n. And with support vector machines, what we have is minimize, again, with respect to our parameter lambda, 1 over n, the sum over all our samples from 1 to n of negative yi, f, this function f, right, the hinge loss. Now we have f here, let me call this f maybe 1 and f0 for when I have positive or negative samples. So I'm going to have f1 for the positive samples here of lambda transpose xi plus 1 minus yi, f0 of lambda transpose xi plus what else? Anyone? What did I have? I already erased that, but what do, oh, well, I have it right there probably. What do I have? Plus lambda over 2n, the sum over all j, say, of lambda j, right? Squared. And this is nothing else than this thing here, which is the same as this thing here, right? I haven't done anything new, except that I have now changed the hinge, the original loss that I had, right? This loss that I had here for logistic regression, right? You see this one? I have changed it for the hinge loss, right? See that? That's it. That's all I did. So it's my SVM solution, which is nothing else than logistic regression. But instead of using the logistic regression loss, I use the hinge loss. And if you rewrite this, you are going to end up with the sum over all I of lambda I squared minus 1 over 2. It's just rearranging the terms over j of lambda I, lambda j, yi, yj, zi transpose zj, right? Which you could also obviously substitute for phi zi transpose phi zj if you want to do it for the kernel space. And does this look familiar? This equation here is the SVM equation that we've derived, right? So you see where SVM comes from once you have these equations from logistic regression. Okay, so let me go back quickly to these slides. So I've added here in the slides the basic equations of the derivations for the support vector machine. Remember, the important thing to remember is you want to maximize this margin. That's why you would see support vector machines and this type of algorithm called maximum margin classifiers because they want to maximize that margin, that distance. This is the derivations that we've defined here. I use rho here in the slides for the margin, same thing otherwise. And these are the equations that we've derived, right? A, I use W on the board and A on the slide, but they're one and the same. Remember, we want to minimize this subject to this other term, right? And we use Lagrange multipliers to do this, and we get the solution. A nice extension, because remember, unless we know what the phi function is that maps our data from a space where our data is non-linearly separable to a space where it is linearly separable, then I may still end up with a space where our data is not linearly separable, even in the kernel space, right? And then a nice extension to these derivations that I did on the board is to add a factor here, another constant, okay, to define what's called the soft margin. And what this variable does, it is 0 for the simples that are correctly classified. They're linearly classifiable with that hyperplane that I finally select, but it's non-zero for the simples that I cannot linearly classify with that linear classifier, right? And with that soft margin, I allow for some small number of these vectors that training simple vectors I have to be misclassified, right? And that's useful when the data is non-linearly classifiable. Final comment, remember that all this that we have derived here for linear classifiers only applies for the two-class problem. We have two mechanisms that are very popular that people use to do classification for multi-classes. One is the 1 versus all, and the other one is 1 versus 1, okay? 1 versus all being more popular than the 1 versus 1, but all of them are popular. Here's another way of addressing this that I've included in the slides in case you want to look at this. It's called the Kesler's construction, and it's just a way to define what we just said. This is y and y minus for the class 1 and class 2. In that case, it would be class 1 and class 3, class 1 and class C, and so on, right? So you construct a set of classifiers, and now you want all of them to be larger than 0. So it leads to a solution depending on what you use, but with the mean square error, it leads to a solution that's given by the pseudo-inverse. No surprises. And that's it for linear classifiers. I'll talk about how to know which classifier is better than the other, how to know which of these classifiers that we're defining, or regressors that we've defined, should we select at every time. We will conclude that there is no classifier that is better than anyone else, but then that will allow us to define methods to work around this problem, okay? And then after that, we'll move to deep networks. All right, see you next time.